In this video, I'm going to go over, to the best of my ability, how to do heat equations, and I'll be going over all four steps. And to start, heat equation consists of four main steps. We have separation of variables, solving an x ODE, which is just eigenvalues, solving a t ODE, and doing a Fourier series and assembling our final answer. So here we have a problem where we need to solve the heat equation, but before we start, we need to figure out what all this means, because right now this means nothing to us. So first let's start with this equation that has partials of u. This is our partial differential equation, and this is used for separation of variables. And if you're wondering where we get this u from, we get it from the function u of xt, which is equal to capital X of little x times capital T of t. And we're basically going to be doing partial derivatives of this function. So for example, for partial of u with respect to t, it could also be rewritten as this, and we'll be treating capital X as a constant, and then taking the derivative of our capital T function, which is just something like this. And this will be used in only step one. Next, we have these two conditions where x is 0 and x is L, which matches our bounds of x being greater than 0 but less than L. And these are our boundary conditions, because they may not tell you this, but in the context of a heat equation, we usually have some rod of length L, and the left end is represented by x equals 0, and the right end is x equals L. And then what these boundary conditions mean are the temperature at each end of the rod. So in this case, at the left end of the rod, the temperature is 0, and at the right end, it's also 0. Now, they could also give you, maybe instead of u of 0t, they could give you the partial of u with respect to x of 0t. And this would happen if either end of the rod is insulated, and if they don't give that to you, then it'll be written as a word problem. But in this case, we don't have an insulated rod, so we don't need to worry about any partials of x. And so these are our boundary conditions, and these are used in solving our x ODE. So this is for step 2. And then lastly, we have u of x where t is 0. These are our initial conditions. And this could either be given as a continuous function or a piecewise function like we have here. And this is used in the final step when we do Fourier series and cosine and sine series, which I'll explain later. So first, let's start with step 1, separation of variables. We have a constant k, and we have the double partial of u with respect to x, and that's equal to the partial of u with respect to t. So first, we'll do the double partial of u with respect to x, and that could also be rewritten as like this form. And if we take if we know that u of xt is capital X of little x times capital T of little t. So for this, we would treat the capital T function as a constant, and then we take the derivative of capital X twice. And then we have this. Now we do the partial of u with respect to t, which could also be rewritten like that. And then we treat x as a constant this time, and then we take the derivative of t. Now that we have these partial derivatives, we can plug them back into our PDE. So we have k times x double prime times t. I'm not going to write the parentheses and all that because it doesn't change anything right now, and it makes it simpler. So we have this. Also, sometimes we'll have a value for k. Regardless, it doesn't matter. And so now we need to separate the variables. We need to put the x variables together and the t variables together. But we also have to figure out where to put this constant k. And anytime we have a constant, it's always going to be with our t ODE. The x ODE can only be in terms of x. So we can divide out the capital X and the k and capital T, which then gives us x double prime over x is equal to capital T prime over k times capital T. And we set both of these equal to negative lambda. So now we have so now we can split this into two equations. We have one where it's x double prime, or capital X double prime over capital X is negative lambda. And we have to put this equation to standard form, which means isolating the x double prime. So when we do that, we can multiply both sides by capital X. That gives us x double prime is equal to negative lambda capital X. And then now we need to bring everything over to the left side, which then leaves us with x double prime plus lambda times capital X is equal to 0. This is our first ODE. Now we need to find our t ODE. And so similar to the x ODE, we have to isolate t prime. And to do that here, we multiply both sides by k and capital T. That gives us this equation. We bring it over to the left side. We bring everything over to the left side. We have t prime plus lambda k big T equals 0. So that's step one. We have two ODEs. Let me just move that up there so we have more space. Now, step two. We have to solve the x ODE, and this is an eigenvalue problem because our goal is to get a value for lambda and an eigenfunction, which will represent our function of x. So to do that, we need to use our boundary conditions, which we know are u of 0t equal to 0, and u of lt also equal to 0. But these don't really help us right now because our x ODE is dependent on x. So to do that, we need to take our boundary conditions and plug them into u of xt, which is just big X of little x times big T of little t. For the first one, u of 0t, we have x of 0 times t of t is equal to 0. So we have to so one of these functions is equal to 0. And for heat and wave equation, we always assume that t of t is never 0 because t is greater than 0. So that means x of 0 is 0. Now if we do that again, for u of lt, we have x of L times t of t equal to 0. One of these equals 0, but once again, t of t cannot be 0. So therefore we have x of L is equal to 0. Now, let's just sum up everything we have. We have our x ODE. We have x of 0 is 0, and x of L is also 0. And now with these conditions, we can use them to find lambda. So for this question, we're going to use x equals e to the mx format. This is just a thing you remember from auxiliary equations from the last exam. I just write this, that's what my TA told me to do. And so then we're left with m is equal to plus or minus negative lambda. And now this is where we can use our eigenvalue cases. Now, my TA said that we're only going to need cases 1 and 3, which is lambda is equal to 0, which is a repeated real root, and then lambda is greater than 0, which is complex roots. So first we'll do case 1, which is just lambda is equal to 0. This means m1 and m2 are 0. And so when we plug them into our equation, we have c1 plus c2 times x, because this is a repeated root, so we can't have the same m value. And now we can just plug in these conditions we have up here. So x is 0, c1 plus c2 times 0 is 0. This cancels out, which means that c1 is equal to 0. Then we can do x of L is equal to c1 plus c2 times L equals 0. Now we already know that c2 is 0. Well, actually, we don't know that c2 is 0. But what we do know is that L cannot be 0, because L is the length of our rod. So you can't have a 0 length. So what ends up happening is you have c2 times L is equal to 0. L is not 0, that means c2 is 0. Both of our constants are the same, which means that this is a trivial solution. And this tells us nothing. We just need to do this to prove that there's no eigenvalues we can find from this case. Next, we can do case 3. And this is where we're going to actually get eigenvalues. We have lambda is greater than 0. And in this case, we have m is plus or minus I radical lambda. Sometimes they like to set this m value equal to like alpha or alpha squared or something. You can do that if you want. I don't like doing it because it just confuses me. So we know that for complex roots, we have our function is equal to c1 times cosine xm, and our m is radical lambda, plus c2 sine x times radical lambda. And now we can, like before, we can plug in our conditions. So we have x of 0. When we plug in 0 to the cosine, that becomes 1. When we plug it into sine, it goes to 0. So we have c1 is 0. Next, we have x of L. Now we already know that c1 is 0, so we don't even need to write that c1 part. So we do c2 sine of L times radical lambda. Now, our first case already had a trivial solution. Here, we need some kind of eigenvalue. So we can't have c2 equals 0, but what we can do is figure out when this thing inside the sine function is 0. Now in general, sine is 0 for n pi, for all integers n. So what we do is you set the lambda, or radical lambda times L equal to n pi. Now what we do is we isolate lambda, radical lambda, that's n pi over L. We square both sides, and then now we have lambda is equal to n pi L squared. We also need an eigenfunction, so we write that as xn, and we plug it into this equation up here. Now we already know that c1 is 0, and we only really care about this sine function because that's where our eigenvalue is present. And so what happens is that we plug that in, and we get, because this is radical lambda, we can drop the square we have here, So it just becomes n pi x over L. That's step 2. Step 3 is a lot shorter, at least for heat equation, because now we need to solve our TOD, which was this. Now we don't have a T double prime, which means we don't have to use all these cases to get our ODE. Instead, we can use integration. So what we do is we bring the k lambda t to the right side, divide by big T, and then now we're left with T prime over T is equal to negative k lambda. And now what we can do is we can integrate both sides with respect to t. So dt plus c, and this is also dt. Now the right side seems pretty straightforward to integrate, but how would we integrate this left side? Well, this t prime is the same as d of big T over d of little t. That means that the d of little t cancel out, and then you're left with the integral of 1 over big T with respect to, or integral of 1 over t dt. And I'll just rewrite this here. So now we can integrate both sides, and we're left with the natural log big T is equal to negative k lambda t plus c. But we're still not done yet because this big T needs to be by itself, and we have to get it out of this natural log. So to do that, we raise both sides. We have both sides. We do the e. We put it to the e to the power of each side, and that gives us our big T, and then e to the negative k lambda t plus c. And then also we could simplify this a little further by bringing down the c, because e to the c can be rewritten as just c. And then also we have this lambda here. That's not good. But we already found our lambda, so now we can actually plug it in. So our t becomes t of n, cn. I'll explain what this cn means later. E to the negative kt, and this fraction that makes the answer hard to read. So that's step 3 done. And now it's time for the Fourier stuff. This is the longest part of the question, and is what kind of confuses me when I was first learning it, but it makes a lot of sense as you go through it. So we know that u of xt is equal to the function of x and the function of t. But we just solved for tn and xn for all integers n where n starts at 1 and goes to infinity. This is a series, so we can say that, or a Fourier series specifically. So we could say u of xt is the infinite sum, where n equals 1, of xn times tn. So I'll write that out really quickly. So we have our x function, and then our t function. Actually, this coefficient, I'll move that to the front. And then just to make it simpler, I'm going to leave I'm going to leave lambda in our E just to make it easier to read, and I'll plug it back in later. So now we have our series, but this isn't our solution yet because we still don't know. We need to find what this Cn is. This is a Fourier coefficient. And if we go back up to our initial condition, we see that our initial condition is when t is 0. So what we can do is we could plug in t is 0 into this series we have here. And then what happens is that the E just becomes 1. And then we now have a very familiar series. If we compare this to what a Fourier series is, we see that we have a coefficient and a sine function. That corresponds to this part of the Fourier series, which means that this is a sine series. So that means this capital C, the Cn, could be treated as Bn as if we were doing a full Fourier series. And then we have the formula for a sine series right here. But there's a problem with this, because Fourier series works for bounds from negative L to L. For heat equation and wave equation, we're usually given bounds of 0 to L, so we have half the range, which means that this is going to be a half-range expansion. And while it uses a very similar formula, instead of negative L to L, we have 0 to L, but we also have this 2 over L, which is so normally we do 1 over L, but because our range is halved, we have to do L over 2, 1 over L over 2, which just becomes 2L, or 2 over L. So now we can do that here. We have 0 to L. Oh, and I forgot to say that this is equal to, well, no, I already put it. It's equal to our piecewise, which we can just write as f of x. And so now, to solve the series, we have to do this integral of f of x times sine n pi x over 2, because this is a sine series with and dx. And because this is a piecewise, we have two integrals. So we can split this up into two integrals. We have one from 0 to L over 2, and that's just 1 times sine n pi x over, oh, this is L, not 2. And then the other one is just 0. So L over 2 to L, 0 times sine of all that, dx. Because this integral is because the sine's multiplied by 0, it all goes to 0, so cancel it out. And so we just have to do this integral here, which becomes 2 over L times, to do the integral of a trig function like this, we can take the reciprocal of what's inside minus the x term. So it becomes L over n pi, it's negative L over n pi, because it becomes cosine n pi x over L from L over 2 to 0. Move that down. And so we just plug in our bounds. I'm going to pull this fraction out. So what happens is it's negative 2 over n pi, because the L's cancel out. And then we plug in L over 2 for x, which makes it cosine of n pi over 2, minus cosine of 0, which is just 1. And this is our Fourier coefficient that we worked very hard to find. Now what we can do is we could take our original u of xt and plug in our Fourier coefficient. And also, because this is a sine series, we don't need to find a naught or an, which is this and this. If you have a cosine series, you will need to find both of them. So what happens is we plug all this in, this very fun function. And then we have to multiply it by our x function from before. And then we multiply that also by t, which is e to the negative kt times lambda, which I'm going to plug in now. So you have that. And then this long thing is our final answer. So this is really long. And sometimes for our initial condition, so they can also give this as a trig function. And if they give it as a trig function, the question becomes very different. And they can also give us what L is. They can give us a value for L. And I'm just going to quickly go over one of those because that was on last semester's exam. And I'm going to get that question. This question was something that we did in lecture today. So in this equation, a lot of the stuff that we solved for is already given. So we have our standard PDE, boundary conditions, and initial conditions, but they already give us our XOD and our TOD. They give us what lambda is, and they give us what xn and tn are. But this time our initial conditions are two cosine functions. And I'll explain how to do that. So just like the last problem, we know that u of xt is a series with xn and tn. And so I'll just plug those in. Now, if you weren't given the if you weren't given this stuff, you could still find them with the conditions they give you. I wrote them out already because I just showed you how to solve for all that. So it's kind of redundant. So when plugging this in, we have this very big function. And now, let's plug in our initial condition and just see what happens. So when we plug our initial conditions, our cosine is unaffected because there's no n in it, or there's no t in it, rather. And then we have this coefficient again, and that's equal to that mess of a function. So now that we have this, we could integrate like last time. But the problem is that, and let me just write out this integration. So we know this is a cosine series. So Cn is an which is this here. And we do that. And then also for this question, we have our L is equal to 3 pi. So here we can just do 2 over 3 pi. Integral from 0 to 3 pi. And then we could do let me just make sure I'm doing this right. Yeah, that should be right. Multiply that whole thing by the cosine of 2n plus 1 times x over 6 dx. So now if we were to do this integral, this becomes a very nasty integral because this could be split up into 2 integrals, and then by a trig identity, each of those becomes 2 more integrals, so you have 4 integrals, which would take a very long time, and it's not what they want us to do. So what we need to do, and the professor did this in lecture, we need to simplify, how could we simplify it so we don't even need to do this integral? Well, what we can do, we don't need any of this. We can focus on our cosine functions on both sides. Because what we want to do now is we want to find some value of n that makes this the cosine function in the series, equal to the cosine function in our initial condition. So for the first one, when n is 3, this cosine and this cosine are the same. And so then what happens is, let's say you were to integrate, which you wouldn't need to. You would do this. And then what happens is, because we have a product, because both of the cosines are the same, it becomes cosine of 7 over 6 times x squared. And then by a trig identity, you could split this up into only 2 integrals, one of which doesn't even have a trig function. And that would be this first one, which I'll explain how to use it when we do wave equation, because I have a question that requires us to use this. But if you were to do it here, because we don't have any constants, any unknown constants, when we solve for Cn, we just get 7, which was the coefficient we had here. So what we can say is that C3, because n is 3, is equal to 7. Now let's do this right side, the minus 4 cosine of x over 2. When n is equal to 1, both cosines are the same. And if you were to do out this integral with the minus 4 cosine, you would also be left with minus 4. So then we have, I'll write it as an because it's a cosine series. You know that a3 is 7, and then a1 is negative 4. And so now we know that u of xt is a series with xn and tn. So we now have, here we have x of x3 and t3, or not t3, x1. And so for our final answer, we will do u of xt is equal to x3 times t3 plus x1 times t1. And so what happens is for this for this first part, anywhere we see an n, we plug in 3. And then on this right side, anytime we see an n, we plug in 1. And then when we do that, it becomes 7 cosine of 7 over 6 x times e to negative 4 t, and then I'll also plug in lambda. You can also write it separately as long as you specify like lambda 3 equals whatever. Actually, no, I'll do that because that makes this easier to read. Okay, so lambda 3 minus 4 cosine x over 2 times e negative 4 t lambda 1. And then let's just quickly figure out what lambda 3 and lambda 1 are. So we know that lambda is 2n plus 1 over 6 squared. So we plug in 3, we end up with which is just, well, it's not over 2, it's over 6. 7 over 6 squared. So our first lambda, and then our second one would be, it would just be 1 over 2 squared. And notice how it matches what's inside of each cosine function. You just drop the x. And then this would be our final answer. So we have our main answer, and then we have the variables we put in because we want to make it look somewhat readable. And that's it for heat equation. That covers pretty much everything. For this first question, I got it from an old recitation, and I posted my TA's solution notes. They really helped. If Merce is your TA, you already have the notes, so don't worry about it. And next video, I'm gonna do my best to explain wave equation, which is very, very similar to heat equation. It's just extra steps.